Hundreds of millions of customers tune into Netflix every day, expecting an uninterrupted and immersive streaming experience. Have you ever thought about what goes behind the scenes? A myriad set of systems and services are involved in orchestrating the product experience that you enjoy while sitting on your couch. These backend systems are consistently being evolved and optimized to meet and exceed customer and product expectation. Today, we would be talking about how Netflix does all these migrations at scale and without downtime. Hello, everyone. I'm Abhishek Pandey. I'm a tech lead at Meta. I recently joined them a month ago. I'm working on the AI ML infrastructure pieces. Prior to Meta, I was at Netflix for about 5 years. I worked in a couple of teams and helped Netflix to scale from 100 million to 200 plus million users. While doing that, I championed a lot of their migration projects, modernized bunch of critical Netflix components, and helped them to steer the wheel on latest and greatest technologies and migrated a bunch of services around that. And most of these services are on the production path. So they were called when you watch your beloved shows on Netflix. Apart from work, I explore nature with my wife and newborn. I have an 8 month old, which keeps me busy all the time. And apart from that, I like to travel and play tennis. I picked tennis during pandemic, and I really enjoy it. And here are two truths and one lie for you. And I'll ask, let me know what you think about it. So I caused a global outage at Uber. Yes, I was at Uber for a couple of years as an early engineer and caused a global outage. Could it be truth or lie? Tell me. I met Roger Federer once, and I have his signature as well somewhere. And I've got fired once as well. Now you need to tell me what's truth there and what is one lie there. Anyways, let's move on. So picture yourself enthralled by the latest episode of your beloved Netflix series, delighting in an uninterrupted high definition streaming experience. Behind these perfect moments of entertainment is a complex mechanism with numerous gears and cogs working in harmony. But what happens when this machinery needs a transformation, right? This is where large scale system migrations come into play. So today, let's talk about some of the challenges that we deal with in doing these kind of challenges, right? So one challenge that we often see is like transitioning traffic. There's a piece of the system that's still running the Netflix in production, and there's other piece of system that we are trying to migrate, or the new system, right? With the major challenge is how we can do this without downtime, without uninterrupted streaming for our beloved customers, right? So we have to do this behind the scenes while keeping the availability up and and make sure that we move to the latest and greatest. Our backend systems are mostly orchestrated. We are a set of thousands of microservices that are working closely with each other to give you that experience that you experience when you watch Netflix. And all these systems are constantly evolving, and we need to make sure that we are we are leveraging the latest and greatest technologies in the tech world, and also making sure that we are migrating them to make sure that we cater to the needs of our customers and our business goals. So focus of today's talk would be on how Netflix does these kind of migration at scale without these downtimes. And I'll talk about some techniques, tools, and strategies that we have utilized over years to achieve these goals. Now, the challenges of these system migrations are, point one would be, these systems are, one of the main challenges is establishing confidence, right? And seamless transitioning the traffic to the upgraded architecture without adversely impacting the customer experience. Now, we need to cater to that very closely because the quality of experience really matters to Netflix. And the other bigger challenge is the architecture of the system. The backend for the streaming product utilizes a highly distributed microservices architecture. Hence, these migration also happen at different points of the service call graph. It can happen on an edged API system servicing customer devices. between the edge and mid-tier services or from mid-tiers to the data stores. Another relevant factor is that the migration could be happening on APIs that are stateless and idempotent, or it could be happening on stateful APIs. So we have categorized the tools and techniques we have used to facilitate these migrations in two high-level phases. Phase one, the first phase involves validating functional correctness, scalability, and performance concerns, and ensuring the new system's resilience before the migration. The second phase involves migrating the traffic over to the new system in a manner that mitigates the risk of incidents, while continually monitoring and confirming that we are meeting our crucial metrics that are tracked at multiple levels. Now, you might be wondering what kind of metrics we track to make sure that we are doing it correctly and wholesomely, right? These metrics could include quality of experience at the measured at customer device level. It could be devices like a TV, a mobile, laptop, tablet, any kind of device that you can run your Netflix on. It could be SLA, service level agreements, that the different microservices within Netflix microservice architectures have it in between services and teams. And the third is business level key performance indicators. We call it KPIs. So these are some of the metrics that we watch for, other than obviously the main metrics around the systems and all of that, like memory and CPU. But these are the top three metrics that makes a lot of sense to watch for. That makes life easier for us to say that okay, we are going in the right direction. Now, one thing that you might think about is like, how we do these kind of migration, how we begin these migrations. Let's say you have a service that you have, let's say the service was running using REST, right, for service-to-service communication. Or you might have a server that has REST endpoints, right, and you might want to migrate that service to gRPC, right? It's an internal service, and you think gRPC is a good goal to have and good thing to have in your service, and you migrate to gRPC. Now, how would you move that gRPC based service and replace that REST service into gRPC, right? So we start with replay traffic testing. Now, replay traffic refers to a production traffic that is cloned and forked over to a different path in the service call graph. It allows us to exercise new or updated system, in this case, the gRPC service, in a manner that stimulates the actual production conditions. In this testing strategy, we execute a copy, or we call a replay, of production traffic against a system's existing and new versions to perform relevant validations. So think of the traffic is coming in production, we cloned it, and now the actual traffic is still going through the old system, or I would say existing system, and the clone traffic is going to the new version of the system. This approach has a handful of benefits. Now, replay traffic testing enables sandbox testing at scale without significantly impacting production traffic or customer experience. Utilizing cloned real traffic, we can exercise the diversity of inputs from a wide range of devices and device application software versions in production. This is particularly important for complex APIs that have many high cardinality inputs. Replay traffic provides the reach and coverage required to test the ability of the system to handle infrequently used input combinations and edge cases. This technique also facilitates validations on multiple fronts. It allows us to assert things like functional correctness and provides a mechanism to load test the system and tune the system and scale parameters for optimal functioning. By simulating a real production environment, we can characterize system performance over an extended period while considering the expected and unexpected traffic pattern shifts. It provides a good read on the availability and latency ranges under different production conditions. It provides a platform to ensure that relevant operational insights like metrics, logging, and alerting are in place before migration. So it gives you a lot of bells and whistles to take care of before you even think of moving things to production. Now, replay traffic testing solutions, it comprises of two essential components, as you can see here in the diagram. On the left, you see traffic duplication correlation piece. So this is the initial step that requires the implementation of a mechanism to clone and fork production traffic to the newly established pathway, along with the process to record and correlate responses from the original and alternative routes. On the right-hand side, you see comparative analysis and reporting. This comprises of, after once you do the traffic duplication, you need correlation. You need a framework to compare and analyze the responses recorded from two paths and get a comprehensive report for the analysis. We have tried different approaches for the traffic duplication and recording steps through various migrations and making improvements along the way. There's nothing like you do one thing and you do it best. We learn on the way. So these include options where replay traffic generations is orchestrated on the device, on the server, and via dedicated service. And we will examine these alternatives in the upcoming sections. So so the one of the approaches that you might have think is for to do the replay traffic generation, it could be device-driven approach. In this option, the devices make a request on the production path and also makes another request to the replay path, and then obviously discards a response on the replay path because replay path is the one that you have the new system is running on, right? Now, these requests are executed in parallel to minimize any potential delay on the production path. The selection of the replay path on the backend can be driven by the URL the device uses when making the request, or by utilizing specific request parameters and routing logic at the appropriate layer of the service call graph. The device also includes a unique identifier with identical values on both paths. This is used to correlate the production and replay responses. The responses can be recorded at the most optimal location in the service call graph or by the device itself, depending on the type of migration that you might be doing. Um, so the device-driven approach is obvious has some downsides, right? That there's one of them is like we are wasting a lot of device resources since it's making two calls for every call, right? One on the actual production path and one on the replay path, as you can see in the figure. There's also a risk of impact on device quality of experience, especially on low resource devices where it doesn't have that many resources. It's very true for devices that doesn't have that much computing power and things like that. Adding forking logic and complexity to the device code can create dependencies on device application release cycle, right? And that generally is slower cadence than the service release cycles. We release services every day, maybe twice a day. Um, but devices, we try to release it once a week, sometimes twice a week, but most of the time once a week. So the cadence is really more on the service side. Um, so since the release cycles that on the devices are slower, it can lead to bottlenecks in the migration. Moreover, allowing the devices to execute untested server-side code paths can inadvertent can make you exposed to an attack surface area for potential misuse. So let's look at the other approach, like how we can do it on the server side of things. So to address the concerns of the device-driven approach, the one other option that you could think of is like how we can do this on the backend systems, right? Like can the replay can be done on the backend systems? So it's very similar as you might think of device, but in this case, there's a service running behind the API gateway that's doing that for you instead of a device. So a replay traffic is cloned and forked in the appropriate service upstream of the migrated service. In this case, the device sends a request to the API gateway as it would. Then the API gateway sends a request to our API layer, and then you have API layer would send this to would clone this to an existing service and to the replacement service. So this is the upstream service that calls the existing and the new replacement service concurrently to minimize any latency issues on the production part. The upstream service records a response on the two paths, which is API. The upstream service here is API. It records the response from the two paths along with an identifier with a common value that is used to correlate the responses. This recording operation is also done asynchronously. You don't want to record it while they're responding to your device, right? So that you don't add unnecessary latency on that part. So we do this asynchronously to minimize any impact on the latency on the production part. The server-driven approach benefit is that the entire complexity of replay logic is encapsulated on the backend, and there's no wastage of device resources, as we have seen in the device-driven approach. Also, since this logic resides on the server side, we can iterate on any changes pretty fast. As I said earlier, devices release cadence is much lower than services release cadence. So we can reiterate on this, we can fix things quickly, deploy it, and go with that, right? And record it again and see what's going on. So it's really a great solution from the device-driven approach. Now, however, we are still inserting the replay-related logic alongside the production code that is handling business logic, which can result in unnecessary coupling and complexity in your code. I mean, if I had to think it in a general way, you might have like if, this condition met, execute on the production path, else execute on the replacement service part, things like that. So you might have like for every request on the backend, do these two requests, right? So you have a complex logic in your code. There's also the increased risk that comes with it, like bugs in the replay logic could have potential to impact production code and metrics. Let's look at one other way to do this as well. What if we have a dedicated service that does that, where you have a dedicated service that the goal of this service is to do the replay, but you're not touching any existing service to add that business logic into it. So this is one of the latest approach that we have used to completely isolate all components of replay traffic into a separate dedicated service. In this approach, we record the requests and responses for the service that needs to be updated or replaced to an offline event stream asynchronously. Quite often, this logging of requests and responses is already happening for operational insights. We use Mantis, a tool that is in-house developed in Netflix, open source as well, a distributed stream processor to capture these requests and responses and replay the request against the new service or cluster while making any required adjustment to the request. After replaying the request, this dedicated service also records the response from the production and replay parts for offline analysis. So this approach, it centralizes the replay logic in an isolated, dedicated code base. We call it replay service. Apart from not consuming device resources, as we have seen in the device-driven approach, and not impacting any device quality of experience, this approach also reduces any coupling between production business, as you might have seen in the service-driven approach, and the bottlenecks there. So it also decouples any updates on the replay framework away from the device and service release lifecycle. So once we have this in place, now you might need to analyze this traffic, right? So once we are running the replay traffic and recording a significant volume of responses, we are ready to do something with it, right? We are ready for the comparative analysis and reporting component of replay traffic testing just gives you that. Given the scale of the data being generated using replay traffic, we record the responses from two sites to a cost-effective cold storage facility. We use Apache Iceberg for that. We can then create offline distributed batch processing jobs to correlate and compare the responses across the production and replay paths and generate some reporting for our developers to look into. Now, depending on the nature of the system being migrated, the responses might need some pre-processing before being compared. So it might need some normalization of the data. For example, if some fields in the responses are timestamps, those will always differ, right? Similarly, if there are unsorted lists in the responses, it might be best to sort them before comparing. In certain migration scenarios, there may be intentional alteration to the response generated by the updated service or component. For instance, a field that was a list in the original path is represented as key value pairs in the new path. In such cases, we can apply specific transformations to the response on the replay path to simulate the expected changes. Based on the system and associated responses, there might be other specific normalization that you might want to do to the responses before you start comparing them. Now, on the comparison phase, after normalization is done, we diff the responses on the two sides and check whether we have a matching or mismatching responses. The batch job creates a high level summary that captures some key comparison metrics. These include total number of responses on both sides, the count of responses joined by the correlation identifier, matches and mismatches, and responses could be good responses or error responses. The summary also records a number of uh, good responses like passing responses and failing responses of each path. This summary provides an excellent high level view of the analysis and the overall match rate across the production and replay traffic. Additionally, for mismatches, we record the normalized and unnormalized response as well. So normalized is like the more processed responses, right? And the unnormalized was like raw responses from both sides to in our big data tables along with their relevant parameters, so that developers can look into it and see um, both raw response and the process response to see where it was failing and why it was failing and fix it forward. We use this additional logging all the time to debug and identify the root causes of the issues driving the mismatches. Once we discover and address those issues, we can use the replay testing iteratively to bring down the mismatch percent to an acceptable manner. Now, let me give you a good example. When we were doing one of the largest migration here at Netflix, that was migrating the whole subscriber data systems from old Cassandra cluster to a new Cassandra cluster, also rewriting a lot of bunch of microservices. The first time we saw these graphs coming out of replay traffic, every field was failing, 100% of them. And we were like, wow, this is like, we need to fix all of them. But, having these insights helped us to, to, to basically categorize them and go for the big meaty fields to see which fields can be fixed quickly and we can iterate on it. It took us a while to fix everything, but having the insight really helped us to go in the right direction. I'll cover this topic a little more towards the end of the slides. So, one last thing that I want to talk about here is like you might want to think about the noise as well. Like a common source of noise arises from utilizing some non-deterministic or non-idempotent dependency data for generating responses on the production replay pathways, right? You might think of like on the playback side here at Netflix, the response payload that delivers media stream for playback session could differ, right? The session responsible for generating the payload consults a metadata service that provides all available streams for the given title. Various factors can lead to addition or removal of these streams, such as identifying issues with a specific stream, incorporating support for a new language, or introducing a new encoding. Consequently, there's a potential for discrepancies in the sets of stream used to determine payloads on the production replay paths. And sometimes you might want to remove these noises in your comparison to make sure that your approach mitigates and the all of these noises to make sure that you have accurate and reliable comparison between production and replay responses. So understanding some sort of your business requirements also helps in identifying these noises and removing them. Now, an alternative method to recording responses and performing the comparison offline is to perform a live comparison. In this approach, we do the forking of the replay traffic on the upstream service as described in the server driven section. The service that forks and clones the replay traffic directly compares the responses on the production and replay path and records relevant metric. This option is feasible if the response payload isn't very complex, such that the comparison doesn't significantly increase latencies or if the service being migrated are not on the critical path. Logging is selective to cases where the old and new responses do not match. Now, besides functional testing, replay tracking also allows us to stress test the updated system component. We can regulate the load on the replay path by controlling the amount of traffic being replayed and the new services horizontal and vertical scale factors. This approach allows us to evaluate the performance of the new service under different traffic conditions. We can see how the availability, latency, and other system performance metrics such as CPU consumption, memory consumption, garbage collection rate change as the load factor changes. Load testing the system using this technique also allows us to identify performance hotspots using actual production traffic profiles. It helps expose critical memory leaks, deadlocks, caching issues, and other system issues. It enables the tuning of thread pools, connection timeouts, and other configuration parameters. Furthermore, it also helps in the in determining of reasonable scaling policies and estimations for the associated cost and broader cost risk trade-offs. We have extensively utilized replay testing to build confidence in migration that involves stateless and idempotent systems. Replay testing can also validate migration involving stateful systems as well, although additional measures must be taken in this case. The production and replay paths must have distinct and isolated data stores that are in identical states before enabling the replay of traffic, right? So as I mentioned, when we were doing the user migration or subscriber migration, there were two data sources, the old Cassandra cluster and the new Cassandra cluster. And we have to make sure that they are identical. So, and to begin the migration, we will always, truncate the new database and move everything from old to new database and start the replay logic to see if they have mismatches or things like that. So they have to be in identical state. The data stores have to be in identical state before you start doing these kind of things. Additionally, all different request types that drive the state machine must be replayed. In the recording step, apart from the responses, we also want to capture the state associated with that specific response. Correspondingly, in the analysis phase, we want to compare both the response and the related state in the state machine. Given the overall complexity of using replay testing with stateful systems, we have employed other techniques in such scenarios, and we'll look into that. So we at Netflix, we have adopted replay traffic testing at Netflix for numerous migrations projects. A recent example involved leveraging replay testing to validate an extensive re-architecture of the edge APIs that drive the playback component of our product. Another instance included migrating a mid-tier service from REST to gRPC. In both cases, replay testing facilitated comprehensive functional testing, load testing, system tuning at scale using real production traffic. This approach enabled us to identify elusive issues and rapidly build confidence in these substantial redesigns. Once you are done with replay testing, we are ready to start introducing how we move these changes to production. So, replay traffic testing gives us the initial foundation of validation. But as our migration process unfolds, we are met with the need for a carefully controlled migration process, a process that doesn't just minimize the risk, but also facilitates a continuous evaluation of the rollout's impact. Canary development are an effective mechanism for validating changes to a production backend service in a controlled and limited manner, thus mitigating the risk of unforeseen consequences that might arise due to changes. This process involves creating two new clusters for the updated service and a baseline cluster containing the current version running in production, and a Canary cluster containing the new version of the service. A small percentage of production traffic is redirected to the new cluster, allowing us to monitor the new version's performance and compare it against the current version. By collecting and analyzing key performance metrics of the service over time, we can access the impact of the new changes and determine if they meet the availability, latency, and performance requirements. Some product features requires a life cycle of requests between the customer-driven devices and a set of backend services to drive the features. For instance, video playback functionality on Netflix involves requesting URLs for the streams from a service, calling the CDN to download the bits from the stream, requesting a license to decrypt the streams from a separate service, and sending telemetry indicating the successful start of playback to yet another service. By tracking metrics only at the level of service being updated, we might miss capturing deviation in broader end-to-end systems functionality. Sticky Canary is an improvement to the traditional Canary process that addresses these limitations. In this variation, the Canary framework creates a pool of unique customer devices and then routes traffic for this pool consistently to the Canary and the baseline cluster for the duration of the experiment. Apart from measuring service level metrics, the Canary framework is able to keep track of broader system operational and customer metrics across the Canary pool, thereby detect regressions on the entire request lifecycle flow. It is important to note that with the sticky canaries, devices in the canary pool continued to be routed to the canary throughout the experiment, potentially resulting in undesirable behavior persisting through retries on customer devices. Therefore, the canary framework is designed to monitor operational and customer KPI metrics to detect persistent deviations and terminate the canary experiments if necessary. Canaries and sticky canaries are valuable tools in the system migration arsenal. Compared to replay testing, canaries allow us to extend the validation scope beyond the service level. They enable verification of the broader end-to-end system functionality across the request lifecycle for that functionality, giving us immense confidence that the migration will cause no disruptions to the customer experience. Canaries also provide an opportunities to measure system performance under different load conditions, allowing us to identify and resolve any performance bottlenecks. They enable us to further fine-tune and configure the system, ensuring the new changes are integrated smoothly and seamlessly. A/B testing is a widely recognized method for verifying hypotheses through a controlled experiment, right? It involves dividing the portion of the population into two or more groups, A and B, each receiving a different treatment. The results are then evaluated using specific metrics to determine whether the hypothesis is valid or not. It's industry, the software industry frequently employs a technique to assess hypotheses related to product evolution and user interactions. It is also widely utilized on Netflix as well to test changes to product behavior and customer experience. A/B testing is also a valuable tool for assessing significant changes to backend system. We can determine A/B test membership in either device application or backend code and selectively invoke new code paths and services. Within the context of migration, think of A/B testing could allow us to limit exposure to the migrated system by enabling the new path for a smaller percentage of the member base. Thereby, you can control the risk of unexpected behavior resulting from the new changes. A/B testing is also a key technique in migration where the updates to the architecture involve changing device contexts as well. So let's also talk about like after completing the various stages of validation, such as replay testing, sticky canaries, and A/B test, we can confidently assert that the planned changes will not significantly impact SLAs or quality of experience or business KPIs, right? However, it is imperative that the final rollout is regulated to ensure that any unnoticed and unexpected problems do not disrupt the customer experience. To this end, we have implemented traffic dialing as the last step in in mitigating the risk associated with enabling the changes in production. A dial is a software construct that enables the controlled flow of traffic within a system. This construct samples inbound requests using a distribution function and determines whether they should be routed to the new path or kept on the existing path. The decision making process involves assessing whether the distribution function's output aligns within the range of the predefined target percentage. The sampling is done consistently using a fixed parameter associated with the request. The target percentage is controlled via a globally scoped dynamic property or configuration that can be updated in real time. By increasing or decreasing the target percentage, a traffic flow to the new path can be regulated instantaneously. The selection of the actual sampling parameter depends on the specific migration requirements. A dial can be used to randomly sample all requests, which is achieved by selecting a variable parameter like a timestamp or a random number. Alternatively, in scenarios where the system path must remain constant with respect to customer devices, a constant device attribute such as device ID is selected as the sampling parameters. Dials can be applied in several places, such as device application code, a relevant server component, or even at the API gateway for Edge API systems, making them a versatile tool for managing migrations in complex systems. Traffic is dialed over to the new system in a measured, discrete steps. At every step, relevant stakeholders are informed and key metrics are monitored, including service, device, operational, and business metrics, right? If we discover an unexpected issue or notice metrics trending in an undesired direction during a migration, the dial gives us the capability to quickly roll back the traffic to the old path and address the issue. So stateful. So we talked about stateless APIs are little less easier to migrate, or I would say little less complex to migrate compared to stateful APIs. Stateful APIs pose unique challenges that require different strategies. While the replay testing technique that we have seen so far it can be employed here as well. But you need to have some additional measures that to build confidence for stateful APIs. The alternate migration strategy has proven effective for our system that meet certain criteria, and I'll talk about that. Specifically for our data model, if the data model is simple, self-contained, and immutable with no relational aspects, our system doesn't require strict consistency guarantees and does not use database transactions. You can adopt an ETL-based dual write strategy that roughly follows the sequence of steps, right? So initial load through an ETL process. The data is extracted from the source data store, transformed into a new model, and written to the newer data store through an offline job. So think of the example that I gave you when we migrated subscribers, right, from old data store to new data store, right? So we extracted data from the source, which is the old Cassandra system. We transformed it into the new data model. So the old data model was big, huge. The new data model was, roughly 20% of that. So you transform into the new data model and written to the newer data store through an offline job. We use custom queries to verify the completeness of the migrated records, right? Now, once you are done with that, you do active or dual write strategy to migrate the bulk of the data, right? As the new writes coming in, you are writing to the both data store. So basically employing some kind of dual write strategy. As a safety mechanism, you can use dials to control the portion of writes that go to the new data store. To maintain state parity across both stores, we write all state, whatever writes are altering the states of a data, we write them to both stores. This is achieved by selecting a sample parameter that makes the dial sticky to the entity's lifecycle. We incrementally turn the dial up as we gain confidence in the system while carefully monitoring its overall health. The dial also acts as a switch to turn off all writes to the new data store if that's needed. When a record is read at the production path, we read from the new path as well. So basically, dual reading. The service then compare the what it has read and basically do the comparative analysis, like consistency check on them, and then emit a log or metric if they fail, right? So basically, you are doing some live comparison analysis, or you can do this offline based on the latency requirements of the particular use case. In our case, what we used to do is like we'll read and then we emit an event. So basically, you read from the old store and emit event to read from the new store, and then do the comparison and emit event when it fails. This process gives us the idea of the functional correctness of the migration. To verify the completeness of the records, cold storage services are used to take periodic data dumps from the two data stores and compare for completeness. Gaps in the data are filled back with the ETL process. Once the data is verified for correctness and completeness, dual reads and dual writes are disabled. Any client code is cleaned up and read or writes only occur to the new data store. So as I talked about cleanup of any migration related code and configuration after the migration is crucial to ensure the system runs smoothly and efficiently and we don't build up tech debt and complexity. Once the migration is complete and validated, all migration related code such as traffic dials, A/B tests, and replay traffic integration can be safely removed from the system. This includes cleaning up your configuration changes, reverting to the original settings, disabling any temporary components that you might have added during the migration. In addition, it is important to document the entire migration process and keep records of any issues encountered and their resolutions. By performing a thorough cleanup and documentation process, it it makes your migration process more bulletproof, so that basically you can go back and see what you might have done, what are the learnings, and you can share it with other teams if they are looking for similar kinds of migration. So you learn as you go. We have utilized a range of techniques outlined today in this talk to conduct numerous large, medium, and small scale migration on the Netflix platform. Our efforts have been largely successful, with minimal to no downtime or significant issues encountered. Throughout the process, we have gained valuable insights and refined our techniques. It should be noted that all of the techniques presented today are universally applicable, as each migration presents its own unique set of circumstances. So, as a parting thought, I want to give you some glimpse of like how we have utilized a range of these techniques outlined today in this talk to do some of the largest migration here at Netflix. Of course, we have used this in medium and small scale migrations, but our efforts have been largely successful in the large migrations with minimal to no downtime or significant issues encountered. One of the examples that I'll give you is like during pandemic, when the pandemic got hit and everybody was quarantined and sitting at home and wanted to watch Netflix, we pulled the plug on the system that was responsible for all your subscriber data, your watch history, and everything. You know, the system that gets the highest QPS here at Netflix, the system that has the largest Cassandra cluster after playback. We have shut down the old system and migrated all traffic to the new system April 2020 while you were watching your beloved shows, while we were getting the tremendous load on our backends. We were able to do that. And have you noticed anything? Nothing. We're not in news. It was an eventless migration. We were in news for good reasons like Tiger King and all, but not for the bad reasons. And I still remember flipping the configuration from the old system, new system. My hands were shivering, but underneath, I was like confident that we have done enough to do this. Same week, we added 38 million subscribers, the largest ever in Netflix history in a week. And this was not possible with the old system. The new system also enabled us to launch a lot of new features like ads tier, gaming handles, live traffic, and all of that, which was not possible on the old system. So migration is necessary, Everybody needs to do migration, but do it in a way that you don't sweat when you are pulling that configuration or shifting that traffic from old system to the new system. With that parting thought, I'll say thank you so much. And if you want to connect with me, obviously I'm no longer work at Netflix. I'm at Meta. But if you want to connect with me, these are my contact details. And thank you so much for you to listening through this talk. I hope you get something out of it and connect when you get a chance. Thank you. Bye.